All right, so we got ramps. So this ramp has to do with a block that is going down the ramp. So it's actually moving. So we might look at it and we might think, oh my gosh, there's a lot of things different. No, it's actually pretty similar to a block that is staying still on a ramp. So we have a crate with a mass of 25 kilograms down a ramp. The ramp is 2.5 meters long and 1.1 meter high. So we see that if we are given a hypotenuse and a side, we can find the angle. So how do you find the angle, right? You have to use your inverse sine equation. So angle is equal to sine inverse opposite over hypotenuse. So when you do that, you should get 23.6 when you put this into the calculator. So let's save that for later. So it says if the ramp is frictionless, at what rate does the crate accelerate? So if it is frictionless, that means the block will accelerate down a ramp. We're not used to seeing acceleration and friction together, but this block will accelerate because gravity is acting on it. And we know gravity is an acceleration, a form of acceleration. So if you draw the free body diagram, you have force normal and force of gravity. Those are the only two forces acting on the object. So I will take gravity and divide it into its components so that it will be both perpendicular and parallel to the incline. So that makes it a little bit easier on myself. So we know that as it's going down the incline, acceleration perpendicular, which is this direction, will be 0. The reason being is that the block travels nowhere in the vertical dimension. However, whenever it's going down the incline, which is parallel to the incline, that means the acceleration will not be 0. So we already know that will have to do with our F net equation. So the block will accelerate down the incline due to F net is equal to ma in the parallel direction. So then I'm going to take my net forces parallel to the incline, which is Fg sine theta, which is seen over here. Okay, I also highlighted it in pink because everything else is perpendicular to the ramp. So Fg sine theta is equal to mass times acceleration. So I'm going to take that. I'm going to solve for acceleration. So you see I solved for it right here. Fg becomes mg, okay? And then mass, gravity, and sine of that angle that we found earlier. So your acceleration down the ramp is 100 meters per second squared, which is a very high acceleration. So this object is accelerating a lot, actually, and we can see that because it's a very heavy object, and this is a sudden acceleration, okay? And this acceleration is actually higher than gravity, so I don't think this is a super realistic problem, but that's what the answer is. So B, if the crate slides down at a constant speed, okay? So we know that if it is at a constant speed, then the acceleration parallel to the ramp is 0. So if we want to find mu, we have to derive equations. So if acceleration is 0, F net is 0. I look at my free body diagram. One force has joined my two forces, and that is friction. So again, Fg is going to be divided into its components, and green versus pink, okay? So pink, which is parallel, we have our parallel forces. They are going to be equal to each other because acceleration is 0. So force of friction is equal to Fg sine theta. Perpendicular acceleration is 0, so F net is 0. So top is equal to bottom. Okay, Fn is equal to Fg cosine theta. So I know I need to find mu. So if I need to find mu, that belongs in the force of friction equation. So I'm going to take equation 1, and I'm going to review mu times force normal. So if I know I want to find mu, I'm going to isolate that, right? And whenever I isolate that, I will divide by force normal. Well, okay, can I solve for mu? I have force of gravity, I have my angle, I don't really have force normal, but I do have it in my second equation, so I'm going to substitute that right there. So when I substitute that, we actually did this problem in class. So my mu going down the ramp is going to be dependent on sine over cosine, because my weights will cancel out. Tangent theta is the same as sine over cosine. So mu is equal to tangent theta. Okay, so tangent of 23.6 is going to be mu is equal to 0.4. So we know that the friction needed for an object to travel down an incline will be dependent on the angle. Okay. All right. If the mu is equal to 0.25, what pulling force could the crate be pulled up the ramp at with a constant speed? So here's my little dude over here. He has a rope. He has a little rope, and this rope provides tension. We also know that there is friction. However, friction is going to be going opposite the direction of motion. The direction of motion is going to go up the ramp. So that means friction is going to go opposite that. So this is my free body diagram before it's been broken down. So now we break it down. Okay, we know that if we want a constant speed, then my acceleration parallel is going to be 0, which means my F net parallel is 0. We also know that acceleration perpendicular is also 0 because the block is only traveling parallel to the incline and not perpendicular. So if I derive my equations, my top is equal to the bottom in green. My left is equal to the right. So that's what we see here. Okay, let's go ahead and move closer. So I get my two equations. Now let's remember what we're trying to solve for. What pulling force? So pulling force is going to be the tension. So I know ultimately I need to solve for tension. So if I want to solve for tension, I'm going to make sure I have everything else. I have my angle, gravity, mass. I don't really have force of friction. But if I go ahead and review that force of friction is equal to mu, I know that I have mu. I don't have force normal yet again. But I do have force normal in my other equation. So what are we going to do? We're going to substitute that. So when we substitute that, I will get my tension equation is equal to all of this, right? So things that will contribute to tension. If you have a greater angle on the incline, then you will have more tension. If you have more mass, more gravity, if you have a greater friction, coefficient of friction, that will increase the tension. So I went ahead and rearranged this algebraically because I saw that mg appeared on both of my components. So I singled out mg and I multiplied that by mu cosine theta plus sine theta. So when I plug everything in, I should get 157.4 newtons. Okay, and that is that.